On IMF problems, we have a few different steps, all of which we will practice through these. First is just stating and knowing what the IMFs are. So recognizing the type of compound or mixture you have and what IMFs it would exhibit. Then we try to understand how strong those IMFs may be, maybe based upon the molecular structure itself or connecting it to some data. Lastly, we do want to then use what we know about strength to predict and explain properties. So this first one with dispersion forces does all of those steps well. It starts by kind of defining what a dispersion force is. So right here, this is my poor drawing of two methane molecules that would be right next to one another. In those cases, the electrons would be fairly evenly distributed between the carbons and all the hydrogens. So there's our nonpolar even distribution of electrons. If one of those molecules has a random shift of electrons towards one side, we would create a temporary instantaneous dipole, where the other one would still be nonpolar and have that even distribution on average. But because of my electrons here on my first methane molecule, it would pull the nucleus a little closer while pushing the electrons away, causing a temporary dipole on the next. That would then cause these two molecules to attract one another. That is kind of the mechanism or the process of a dispersion force, a temporary dipole that then induces dipoles on molecules around it. As we start to look at different molecules, we can see this dispersion force and its effect. The first comparison is a chlorine molecule to an iodine molecule. Both are perfectly nonpolar bonds, like the H2 in the notes, meaning that on average, the attraction is perfectly the same and the electrons are shared perfectly equally. Iodine has way more electrons. It has over 100 electrons compared to 30-something for the CO2 molecule. That makes it more polarizable. That means that that electron cloud, as it shifts back and forth, maybe randomly, can create a larger temporary dipole and induce a larger dipole on a neighboring molecule. That increases the dispersion forces, and this also turns into properties. At room temperature or under standard conditions, iodine is a solid, whereas chlorine is a gas. So definitely connecting these beyond just the prediction to a property that supports our prediction. Isomers here means two different forms of the same molecule. Pentane and neopentane both have the same formula, C5H12, meaning they have the exact same number of electrons, the exact same number of bonds, and of each atom. Both of these are just carbons and hydrogens, meaning they're both nonpolar. So the only attractions or only forces between them are dispersion forces. Pentane is a longer, larger molecule with more surface area, or it's more spread out. The more surface area we have, or the more spread we have across our molecule, the more polarized it could be, or the more places that the molecule can interact with other molecules of itself, creating a stronger dispersion force. So when we look at two equivalent formulas, the more spread out version would be able to have larger dipole attraction or dispersion attractions. Excuse me. C2H6 and C2H2 are pictured over here. These would be ethane and ethyne or acetylene. All of these are single and these are triple bonds. That higher bond order, which means going from the double or the single to the triple bond, means that we have electrons in pi bonding orbitals or we have pi bonding. That sort of electron sharing is easier to polarize. It's not as strongly attracted to the nuclei there. So when there is some of that back and forth shift, it can be a little bit more than within a single bond. So because that one's more polarizable, we are going to see greater dispersion forces there. There are slightly fewer electrons here, but the double and triple bonding is more important in this case. So if we were to compare these for pentane compared to neopentane, we would see higher boiling and melting points, and we would see maybe a lower vapor pressure. Here, same idea with ethyne, lights off, where we have higher attractions. And the question here is, why do we have dispersion forces pretty much no matter what? Well, dispersion forces are the result of that random motion of electrons. All atoms have electrons. All molecules have electrons. And electrons are always in that constant random motion. So we're always going to be able to form a instantaneous or that temporary dipole no matter what types of atoms we have. Not all molecules have permanent dipoles or have an ion, like an ion dipole, or a hydrogen atom bonded to the right element for any of our other types. So it is everything that has the electrons and has the electrons in motion. That means that they can, all have dispersion forces.